Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, everyone. It's my pleasure to introduce Jenny Finkel. She's a graduating student from Stanford University, working in the natural language processing group. She has done exciting work on core natural language processing problems like parsing, named entity recognition, coreference resolution. And we overlapped a little bit at Stanford, so it's a great.
Used to play poker together?
Sorry?
Used to play poker together?
Okay, this is yes, we
Sorry.
did, and she was winning. So let's hear her talk.
I think pink I mostly won. Hey everyone. So yeah, I'm going to talk about stuff that I did during my PhD. And feel free to, interrupt with questions, clarifications, etc. Does the space not work? There we go. All right. I guess you guys are mostly NLP people, so I probably don't have to give you quite as much motivation for NLP, but I'm going to give you a little bit anyway. And so in my head, the goal of NLP is to understand language. But I put that in quotes because I'm somewhat a pessimist that we're going to have, pure semantics one day. And I think that this notion of understanding is really just going to manifest itself in the kinds of NLP applications that we make, and that, to get them right, you need semantics, at least in some sense. And so things like, machine translation and summarization, a lot of bio-NLP work where you're trying to get information from papers into databases to help the bio people do their work. Sentiment analysis, which probably also goes along with things like summarization. So if you want to get, Yelp, instead of reading 120 reviews, you just want to get one, bit of overview for a review and the general sentiment behind all of them. Question answering. I think in the future, speech interfaces for things like, cars and robots and stuff are going to be really common. And so all of these require some level of understanding. And, to understand a sentence, you need more than just the words that you have. And so here's a sentence that I took from a Polish news site during the Olympics. And I just went and I found some Polish English dictionary, and I took the first definition of every word, and I got something that was pretty nonsensical. It says, property terrestrial on Stachowizny was still on ages. If you put it through an actual machine translation system, you actually don't get anything that's a whole lot better. I think you get estate in Stachowizny was in the Middle Ages. I got a Polish speaker to tell me what it actually translates to is that this Stachowizny estate was established in the Middle Ages. But the idea here is that there's a lot of structure and there's a lot of things going on more than just the words. And so to do a good job at most NLP tasks, you need to uncover a lot of this internal structure. And so, like I said, to do any sort of high-level understanding, you're going to need a lot of low-level processing. And so imagine you're building something like, just a fact finder. You're trying to generate facts about Obama, for instance, and you've got this sentence from Wikipedia. And it says, Obama is a graduate of Columbia University and Harvard Law School, where he was the president of the Harvard Law Review and where he received a doctorate in law. And so what are the things you have to figure out here? You need to figure out that Obama is a person, so you need to do named entity recognition. You need to figure out that Columbia University and Harvard Law are universities or organizations, so that's also named entity recognition. You need to figure out that these two references of he actually refer to Obama, so that you can know that Obama was the one who was the president of Harvard Law Review and that Obama was the one who received a doctorate in law. You're probably also going to want to parse the tree. Here's a bit more zoomed in version, but you're going to want to parse the tree so you can get the structure, so you know how the different bits of the sentence relate to each other. And so there's a lot of low-level tasks that you need to do in order to pull out the information that you care about. And so the main question that I've been asking myself over the course of my PhD is, how do we improve these core language processing tasks? Because in my mind, we really need to do a good job at these before we can get to the more interesting higher level stuff. And I focus on, obviously there's quantitative improvement, so each of these kinds of tasks has an evaluation metric. So, for named entity recognition, you've got F measure, and for parsing, you've got eval B. but also somewhat of a focus on what I call qualitative improvements. So things that may not come up in the actual number that you get, but that are really important. And so things like if you're going to do both parsing and named entity recognition, you're going to want the phrases that are extracted by both to coincide with each other and not be contradictory. You're going to want things to be labeled in a consistent manner. There's just a lot of things that come up that don't just manifest themselves in one arbitrary number based on an evaluation metric. And so how do humans do these kinds of tasks? So I'm going to give you an example here where I'm actually going to get you guys to do named entity recognition. And so I've got the Wikipedia article for Princeton, but I'm not telling you if it's a location or the organization. You've got just the word. You probably can't yet tell what it is. I'll give you the whole first sentence. So the history of Princeton goes back to its establishment by New Light Presbyterians. Any idea yet? It's probably not a person, but whether it's location or organization is not yet clear. If I give you the rest of the article, now which one is it? Yeah, it's the university. And so there's a lot of ways you could have figured that out. I think one of them is to recognize that College of New Jersey is a university. That's pretty straightforward based on the word college. So you do named entity recognition, and then you do co-reference resolution to realize it's co-referent with Princeton, and now you've got that Princeton is an organization.
Train Presbyterian ministers.
Yeah, there's a lot of ways you could have gotten it. That's one of them. But the idea here is that all of them require some amount of long distance and multiple levels of information. So you need to do some sort of holistic processing here of the entire paragraph in order to figure out what Princeton is. Computers, on the other hand, are very myopic in how they do a lot of language processing tasks. So still sticking with the theme of named entity recognition, here's an example from some actual data that I had. It's an article about a plane crash in Russia. And it says, they were all Russians and Ukrainians coming to work in the mining towns of Barentsburg and Pyramiden, blah, blah. We know many of the people who live in Barentsburg. Some of them could have been, et cetera, et cetera. And so we're going to find person, location, organization, and nationality. Really, it's miscellaneous for you people who know Connell. And so I want to use a named entity recognizer. I'm partial to the one I wrote, so that's the one I ran it through. So this is an actual output. So just to give you the notation, what I have right now is the correct answer. So the reds are locations and the greens are nationalities. And then the shaded answer here is what the classifier came up with. And so it got Russian and Ukrainian both right. That's not surprising. And it got Pyramiden right. And it got the first two instances of Barentsburg right, but it got the second two instances of Barentsburg wrong. And so the question, of course, is why did it get the first two right and the second two wrong? And it's because I think the word Barentsburg, it's not clear at all from the word, just looking at it. It could be a person, people's last name is Endenburg all the time. It could be a location. So you need to look for contextual clues. And the first two have really strong clues really close by. So the word town and the word live, 2 words away. But the other two don't really have any strong contextual clues. And so the classifier just had to, make a guess. And if you look at the actual probabilities that come out, for the ones that I got right, it was, 99% confident, probably even higher than that. And for the ones that I got wrong, it was like a 60-40 split.
Is the word place outside the window?
So this comes up a lot. So it's got Barentsburg is an even grimier place. The thing is, the word place is far away, and you could imagine it saying Barentsburg is from an even grimier place. Like, it's just not quite strong enough. If you knew the parse structure, you may be able to figure it out. But just having the word place nearby is just, it's not enough. I mean, it had access to it, and it wasn't a strong enough clue. And so, the stuff I'm going to talk about is trying to get computers to do NLP in a bit more of a human-like way by looking at long-distance information and multiple levels of information at the same time, or what I'm calling holistic language processing. And so here's an outline for the rest of the talk. I'm going to talk about 3 different projects that I've worked on. The first one is holistic processing across sentences. And so this is adding long-distance information to local models. And this will be related to the named entity example that I just showed you. The second section is going to be the longest part of the talk, and this is holistic processing across tasks. And specifically, I'm going to talk about joint parsing and named entity recognition. I'm also going to talk a little bit about discriminative parsing in there and some more recent work. So if you guys saw the NACL talk on the joint parse and NER, there's actually a bunch more stuff after that. And then lastly, holistic processing across datasets, or what I'm calling multi-domain learning, so domain adaptation, but where you actually care about all of the domains and not just you don't just have a target and a source. And then I'm going to conclude. So let's start with the first part. So like I said, modern named entity recognition systems are pretty myopic. And so the state-of-the-art model is a linear chain conditional random field. I'm guessing most of you probably know how they work already, but I'm just going to briefly go over them in case some of you don't. And so you have a node that corresponds to each word, and that's going to be the label for each word. And so this is the correct labeling. So X is just saying that it's not an entity of any type, and L means it's a location. The lines indicate dependencies. And so if two nodes are connected, that means that when you're making decisions, you know you have access to the label information about the people that you're connected to, but not the other nodes. And so, for instance, looking at this bottom version of Barentsburg, you can see that when deciding what label to give Barentsburg, you have access to the label for the word air and access to the label for the word is, but what you don't have access to is the label for the other time that you saw Barentsburg. And that's really the thing that you want. And so the question is, how can we add that kind of information in so we can get this useful long distance information? And because we don't have it, the classifier ends up labeling it a person instead of a location. And so just to convince you that this kind of long distance information is useful, this graph is pulled from the Connell dataset, and what it's telling you is for every word that I've seen, if I see that word or phrase again, is it labeled, what is it labeled as? So this is saying that there were 3,141 times that I saw some phrase as a person, and for each of those, if I saw it again, there were 3,450 people that occurred where the phrase occurred more than once, and 3,141 of those times when I saw it the second time, it was still a person. 4 other times it was a location, 5 other times it was an organization. And so the main thing that you want to take away here is that there's a really strong diagonal. So if you see a word labeled as a certain type of entity once, and then you see that word again, you're very likely to label it as that kind of entity again. And the one exception here is that there is a lot of mass on this location organization thing, because frequently locations occur inside of organizations, so University of California, or locations and organizations will actually be the same thing because of things like sports teams. Lucy?
The same document, or is this across the corpus?
This was, I believe this was across the corpus. But I'm actually not positive of that.
I always wondered what the within document numbers would be. Do you ever first see it once in the document as location and then subsequently as the organization?
My guess is that for the ones where it's the exact phrase, within document is going to be much stronger, but probably locations within organizations are still going to be pretty common within the same document, because you talk about some school by the place that it's in, and then you talk about the place that it's in.
The University of California is typed twice.
So in the data, so this is just the way annotators have chosen to label data. It's just labeled as an organization.
So the whole thing.
The whole thing is labeled as an organization.
California also within it?
No.
No.
So you should. I've actually done work on nested named entity recognition to deal with that, but the standard corpora just ignore all nested entities. I actually think it's an unfortunate fact about them. But
the model would label every word in University of California as a location. I mean
organization.
Organization.
Yes.
Yeah.
And that gives you full credit. If you label California as a location there, you'll actually lose points. Okay, but the point was just to convince you that there's strong information here. I think we've done that. Okay, so what do? We want to add this long distance link. How do we actually do it? So what's the problem? The problem is that when you have a linear chain CRF like this, you use dynamic programming to reason about the model. And so you're dealing with sufficient statistics for pairs of words at a time. So you start off with this thing, and you compute what you need to, and then you move on to the next pair. You compute what you need to, you move on to the next pair. Compute what you need to move on to the next pair. And now we're going to have a problem because we've got this spurious link here, and we can't do dynamic programming anymore. It's going to fail. But what we can do is if we know the labels of everything else except for this version of Barentsburg, it's very easy and quick to compute likelihoods of just that word. And so you can come up with the distribution for that word conditioned on everything else. And you can see that location is going to be much more likely than person here because we know that long distance link. And so you could just put the most likely thing in there. But that's actually not going to do very good if you're just being greedy the entire time. There's a reason why we use dynamic programming. But instead what you can do is you can take this distribution and you can draw a sample from it. And so you can initially label everything with something intelligent or something not intelligent. And then you can do this random walk where you're constantly resampling labels conditioned on the rest of the labels that you've seen. And so what you do is you pick a node, you erase its label, you keep all the rest of the labels, you compute that distribution, and you draw a sample. In this case, it's probably almost always going to pick not an entity because the word in is almost always not an entity. And so you walk around and you keep doing this, and now we're going to get back to this Barentsburg, and sometimes you're going to get it wrong. It was 15% likelihood that it was a person, but you keep going around. You're going to get back to it eventually, and as you take enough samples, you're going to end up labeling a location far more often than anything else. And so if you do this, you can end up, efficiently incorporating this long distance information in by just generating a lot of samples instead of doing exact inference.
Lost.
Okay.
Where did you get that distribution a couple slides ago? Said 67%.
So I'm only talking right now about how we're doing the inference in the model.
So where did that come from? That distribution.
So how did I learn it?
Yeah.
Okay, so this is something that I've entirely glossed over, but I'm happy to answer it. So the way that we trained the model was training the sequence model separately, so training a linear chain CRF without the long distance, and then learning a model for long distance information, and then basically formulating it as a product of experts. So you can multiply the two different distributions together, and then you end up with a distribution that incorporates both the sequence information and the long distance information.
Is that based on of all the things, how did you know to make that link instead of any other possible link? Because it was the same word?
So because of the way that we've actually, you can link it to things that are the same word. You can link it to other things that are labeled as entities. You can actually, because we're only doing this at test time and not at training time because we're training them separately, effectively what actually happens, even though I haven't drawn it that way, is you can really view it as Barentsburg being linked to everything, but you just don't care about most of the links. You only care about the ones that there's some reason why you should care about them and you incorporate them in. So if you look at it and you say it's the same word, okay, you're going to use that. But if it was a multi-word, say it was, Barentsburg place or something, so it was a two-word phrase, you'd really want to be able to link to all of it, and you don't necessarily know beforehand how big your phrase is. And so as you're doing really, in the actual hardcore math, it is as though everything is connected to everything, but most links provide no information. And then you figure out which links you actually care about, and then you compute the long distance information based on those, and then you multiply it with the likelihood based on the sequence model. Did that make sense?
Still pretty fuzzy.
It's like a trigger model, right?
What model?
Trigger.
Similar to trigger model or cache model. But in your talk, it seems that the trigger pairs are not predefined. It can trigger every word pairs can be triggers, right?
Yes.
I just don't know in the training time how you.
So that's what I was saying. So I'm only talking about test time right now. At training time, the way it works at training time is we train a sequence model, we just ignore the long distance stuff, train a CRF, you learn all the local context stuff you care about.
So
then using that chart that I actually showed you, you compute the likelihoods for two phrases that if, what's the likelihood that they're both person versus that this one's a person, this one's a location. And so you can form these long distance probabilities that way. And we just did that by taking counts. And then, at test time, so I've sampled this version of Barentsburg. What I do is I look around the rest of the document and I figure out where else do I see this phrase, where in this case the phrase is only one word. But if the phrase had been two words, I would look for every place I've seen that phrase or subbits of that phrase or things where this phrase is a subversion of that phrase. And then I would add those links in that case. And then I would do the product of experts and renormalize, and then I would sample based on that.
This distribution is generated from a local model or decouple.
This is generated by multiplying the local model by the long distance model and then renormalizing.
Anytime you only run the local model, right?
Yes, at training time we train them separately, and then at test time we combine them.
I see.
It's more. So it's actually. So let me just get to the results since I'm sensing a little bit of skepticism about training them separately from testing.
So this is testing, okay.
Sorry. So we did compare it to, I guess we actually should, I'll skip to the next one in a second. So this is for Connell named entity. So this is the Connell NER data. We compared so Bunescu and Mooney just did a model that had no links between anything and then only joint information. They didn't have the sequence information at all. And then we compared to just a baseline CRF, so we just train the sequence model and ignore the long distance, and then the model where we add the long distance. And we got about a 10% reduction in error. So most of the time, this did work for fixing most of the consistency issues. Occasionally, you will take something that was right and make it wrong, but far more often, you will take something that was wrong and make it right. We also applied it to a different data set, the CMU seminar data set, which is actually a slightly different task. And here we compared to Sutton and McCallum's skip chain CRF on the exact same data. And so they have something similar where they have a CRF and they add the long distance links and they train the long distance links. They train the long distance model. But the problem is, like you said, in that case, they have to decide beforehand everything that is getting linked. And that's problematic because a lot of the times you don't know what you want to link. And also because of the fact that they're training it that way, they have to use loopy belief propagation, which I think has a lot of problems with convergence and doesn't always give you the right thing. And so even though you could argue that we should have trained them together, we actually got a bigger performance boost from a stronger baseline by doing them separately. And I think it's more efficient. It's certainly more efficient at training time.
What's the difference between your baseline and their baseline?
So they went from 90.2 to 90.6, and we went from 91.8. So theirs is just a linear chain CRF. I'm just better at feature engineering than they are.
Their baseline.
Yeah, so that's what I'm saying. I got a larger improvement from a stronger baseline. So it wasn't just it's not like I got more improvement from a worse baseline. I mean, it was a harder baseline to improve on.
It uses local models, right?
Yeah, as does ours. Both of the baselines are just a linear chain CRF. Ours just has better features than theirs, so it does a better job without dealing with the long distance stuff. If that still doesn't make sense, Bob, we're also meeting for an hour. Okay, so to summarize this part of it, adding the long distance information between nodes that make sense to add them between, you get rid of about 10% of the errors. Given that we were only focusing on a particular type of error, which are these consistency errors, I think that's pretty good. And we basically got most of them. There's other kinds of errors that still exist. And it's a pretty generally applicable technique in that you can train the model and you can add long distance links and then you can use approximate inference, so Gibbs sampling to reason about the model. Okay, moving on to the second part, holistic processing across tasks. So here I'm going to talk about joint parsing and named entity recognition. And so the motivation is that different kinds of information should be able to influence each other. And so here's an example from data. Don't worry, you don't need to process the entire parse tree. But it's always hard to find examples that actually fit on a slide. So this is a fragment of a sentence, and it says, members of the Egyptian Islamic Jihad with ties to Osama bin Laden. And the named entity recognizer correctly got that Osama bin Laden was a person, but it also thought that Egyptian Islamic Jihad was a person, which is wrong.
Question.
Yeah.
So in the previous task, so something like Osama bin Laden, is it tagged, each word is tagged separately?
So the CRF model tags each word separately. At evaluation time, you need the entire phrase. So there's a little bit of a disconnect between evaluation and model.
Just use the P tag, or it's like beginning of P, middle P, end of P?
So there's a bunch of different annotation schemes. My experience has been that you get nothing from adding in the beginning, internal, or single word stuff. Lots of people add them in. I honestly think you're just increasing your label space and complexity, and it doesn't buy you anything. Say that again?
You may not have enough training data to make that.
Yeah, well, you could link it's very easy to tie the parameters to share features in that case. So if you have just a generic CRF that you downloaded, chances are it will learn totally separate weights for each of those beginning, internal, single word models. It's possible to link the features between them also so that some stuff is specific to beginning and some stuff is irrelevant to whether it's beginning or middle. But I've actually played around with all that a bunch, and it makes no difference, is my opinion. But okay, so it screws up this named entity. It thinks that it's a person. It also screws up this prepositional phrase attachment, and it thinks that the ties to Osama bin Laden go with the jihad instead of with the members. And so there's a couple mistakes, and the hope is that we should be able to fix them both at the same time by sharing information between them. And so, yeah, okay. Oh, and the other thing, sorry, it gets one more thing wrong. It adds some internal structure to Osama bin Laden. So it thinks that Osama bin is a phrase within Osama bin Laden, and that's just wrong. It should just be flat.
What is the NML tag?
So NML is nominal. So this is from the Ontanotes corpus, which added NML. So it allows you to encode left branching structure. It does a bunch of stuff, but mostly it's left branching structure within noun phrases. And so it's trying to add some here when it shouldn't. It's very similar to an NP, though. So here's another example from data where it says, like a gross of $1 billion last year. And the named entity recognizer put $1 billion as a unit of money. And then here's the parse tree that the parser got. And once again, you don't need to look at the whole parse tree. What you need to notice is that it has $1 billion as the phrase. And so it's not the case that $1 billion is wrong for what you're labeling as money. It's just the case that if you were to give both of these, this set of annotations to some higher level system that's trying to reason with it, it's going to have a conflict between $1 billion being a phrase and $1 billion being a phrase. And so really what you want is you want it to be $1 billion as the unit of money. And I would also argue that that's a slightly better labeling because it actually tells you that it's $1 billion. But mostly, I think the important thing here is consistency. And so the hope for doing both of these together is that you can get this more consistent output, which is going to be more useful for higher level systems, while at the same time improving performance on both of the tasks. That's the hope. And so the representation that we used was just to augment the parse tree. And so here's just the little phrase for ties to Osama bin Laden. This is the correct parse tree. You can see that it's now a flat noun phrase instead of the spurious nominal. And what we do is we take the root of the phrase that corresponds to Osama bin Laden, augment it with the fact that it's a person, also augment all the children with the fact that they're person, and give the root a special label so that you know it's the root and not just part of a person, but actually the entire person. And so, okay, so we've now set this up, this joint parsing and NER problem, as just a parsing problem. We've turned it into a parser. So there's a bunch of other stuff we're still going to need to deal with to get it right. So for those of you who aren't parsing people, typically the way you learn a model like this, a parsing model, is you decompose the likelihood based on the little subtrees. And so you're going to learn the likelihood of a noun phrase goes to noun phrase prepositional phrase, or the likelihood of a noun phrase goes to a plural common noun, or the likelihood that a prepositional phrase goes to a preposition followed by a noun phrase that's also a person. And so typically, when people do this, they use generative learning, and so they just take counts. And so that when they're computing the likelihood of a prepositional phrase goes to preposition and followed by person, they just count the number of times they've seen the rule, and they divide it by the number of times they've seen the parent of the rule. But now, because we've taken the state space and expanded it with all this named entity information, you're going to run into big problems with sparsity, where you really want to be sharing information between different rules. And so specifically, if you look at this part of the rule that has noun phrase dash person, and then you think about the fact that you could have a similar rule, so prepositional phrase goes to preposition, that's an organization, or prepositional phrase goes to preposition and just a vanilla noun phrase that's not an entity, you really want to share information between these three rules. But the way it's set up where you're taking counts, it's just the information's not being shared, and that's a problem. And so instead of doing generative learning where we take counts, we're going to switch to discriminative learning, which is feature-based, so that we can pull out the relevant features so we can share information. And so the way this works is you've got the phrase, you've got the rule prepositional phrase goes, or PP goes to preposition, NP person, and then you pull out whatever things you may be relevant for the classifier to help it improve performance. And so you can pull out things just like the rule ignoring the named entity information, and so that's the second one. Or you can pull out what's the parent of the rule. Or you can pull out the phrase that the NP person dominates. And so you can say Osama bin Laden is a person and ignore all the syntactic structure. And you can pull out whatever you want here. This is feature engineering. And then the classifier is going to learn weights for each of the features, and then you sum them up to get some number, and that's going to be the score for that particular rule. And then you do that for the entire tree, and you add them up, and then you can normalize over all of the different possible parse trees. And so instead of having a probability like we had when we were taking counts, instead we have scores, and then you normalize over the entire tree to get a probability. But the idea is that we're using features now instead of just taking counts of the number of times we've seen rules. And so we're going to take a slight detour at this point to just talk about discriminative parsing without the named entities, and show that discriminative parsing helps parsing in general without dealing with the joint parse NER. And so for these experiments, we just use the Penn tree bank, which is the standard parsing corpus. For the grammar, we just stuck with so the grammar is the set of allowed rule subtrees. So you can't just pull out every single label and make every single possible rule that you can think of, because it just becomes computationally intractable, because there's thousands of rules, and then you end up with, there's thousands of labels, and then you come up with things like billions of rules. So we just pulled out all the rules we'd seen in the training data and used those, and that was it, which is the standard approach in parsing. And then to do the numerical optimization to actually train the weights, this was still very, very slow. And so we heavily parallelized the whole process, and we used stochastic optimizations. And we ended up with the first results on non-toy data for a discriminative parsing model. Chris?
So just a quick question. Do you do any markup before you extract the grammar? Because that's kind of standard.
Yeah. So we binarized the grammar. I think it was 1 level each for horizontal and vertical markavization. And I tried a couple different ways of binarizing, and I ended up just going with right branching because it was just simpler and it made no difference. So yeah, that's why you end up with thousands of rules, is because of the binarization and the markavization. Yeah, okay, so then we had to do a whole lot of software engineering or systems engineering to actually get it to train in a reasonable amount of time. And so using the same grammar, if we trained just a vanilla generative PCFG, we got about 83%. And the feature-based discriminative parser got about 89%. If you just did discriminative parsing where the only features were the rules, you end up, I think it was at about 85 or 86%. And so you got some benefit from switching how you trained, and then some benefit from, or a lot of benefit from adding the features. So the features are really important here. I actually think might have even been, yeah, it was about 85%, I think. So you get more gains from adding features than from switching your training regimen, but both of them are important. Okay, so now I've hopefully convinced you that discriminative parsing makes sense. And that's what we're using for the joint parse NER model. But the joint model needs a more expressive grammar. And so when we were just doing parsing, we just pulled the rules that we had seen in the training corpus, and those were all that we used. But in this case, when we tried doing that with the joint model, it crashed and burned because the label space is now a lot sparser, and so there's a lot of things you haven't seen that you actually really care about. And so specifically, you'll see things like you'll have a rule that you've seen, say, with a noun phrase that's a person, but you've never seen it with a noun phrase that's an organization, or you've never seen it with just a noun phrase that's not a named entity, and you're going to want to add all of those in. But you can't add in everything because, once again, it gets too slow. And so what we ended up doing was selectively adding new rules that we had never seen in the training data based on things like the presence of a noun phrase in the rule, since noun phrases tend to co-occur with named entities. And so if there's a noun phrase, we just make a copy of it with every single kind of named entity augmented. Or if we've seen a rule with one kind of entity, we just make copies of that rule with every other kind of entity. And we tried adding a bunch of other ones that seemed sensible, but we found that this set was the nothing. Adding anything else only made things slower. They didn't actually make them better. So all right. So how does it do when we do the joint model? So here I'm using the OntoNotes corpus. I don't know if you guys are actually familiar with this corpus. It's relatively new, and to be honest, I'm really surprised it has not gotten more attention in the NLP community. But this data is labeled with parse trees, named entities, coreference information, word senses, and semantic role labeling. It's the same data that's been labeled with all of them. But we're only using the parse and the named entity portions here. And it's split up into different sections. There's, I think, a couple of different languages. I only worked on English. And then it was just broadcast news divided into different corpora based on where it came from. And so this graph shows you so this is just the named entity results right now. Parsing is on the next slide. And so I'm showing you for each of the different sections. And they're much smaller than the Penn tree bank. So they range in size from about 500 sentences for MNB and NBC to about 5,000 sentences for CNN. I actually don't remember what MNB stands for. I think I know all of the rest of the acronyms, but not that one. But it's broadcast news of some sort. And so, as you can see, the joint model helps the named entity recognition a lot. I think the largest gains that we got were about 22% reduction in error. Obviously, we got bigger gains when we started with weaker baselines, but we did improve significantly on all of the different sections. Parsing wasn't quite as happy of a story. We saw improvements in 5 out of the 6 corpora, but we saw, I think there was one case where, in NBC, the joint model actually did slightly worse, and the places where we saw gains were much smaller. So I think the biggest reduction in error that we saw was about 6% here. But this story is going to get a little bit happier later on. We are going to get better performance as we keep going through the talk. But right now, you can see you get a little bit of a gain, but it's not huge for parsing. But we got much bigger gains for named entity recognition. And so, like I said, up to 6% for parse errors and up to 22% for named entity errors.
For name entity, what's the baseline?
I mean, the baseline depends. Oh, what's the baseline model?
Yeah.
The baseline model was a linear. So the baseline model was a linear chain CRF for named entities. It was a discriminative parser for parsing, and then for the features, so you can actually.
Do you use parsing features?
In this example, no. I mean, I have tried to do NER with parsing features before and not had a lot of luck, but that was different experiments from these ones. But we did use the exact same features. So you can you can actually encode features from a linear chain CRF into a parser, like almost perfectly. It's not a 100% mapping, but it's really, really close. There's only a couple kinds that you can't transfer. So it was the same parsing features in the joint model and the same named entity features in the joint model, and then the only additional features were a few features over the joint structure, so the joint rules and the joint labels, but mostly it was the exact same features.
So it was the named entity memorized that you talked about in that earlier section.
So the CRF, it's the same. It's an equivalent model. It's just it's trained on a lot less data, so it's not doing as well. But the model is equivalent. Yeah. All right. So the kinds of errors that we got. So the biggest ones were for the named entity recognizer. A lot of things where it had gotten a boundary wrong before, it got right now. And so here's a case where you see the word Bill at the beginning of a sentence. Bill can be a name. It can also be a common noun. It's capitalized here, but it's at the beginning of the sentence. And so it sort of ends up thinking that it's a common noun instead of a proper noun. So I think about 17% of the boundary errors got fixed. Similarly, there were lots of cases where the baseline named entity recognizer correctly got that some phrase was an entity, but it just got the type of entity wrong. And so here it thought that New York was an organization. Presumably this is from one of the small corpora where it actually hadn't seen the phrase New York before. And the joint model got it correct. We got a little bit better syntax, like I said. Most of the improvements came in the noun phrases, those NML or nominal phrases, and in prepositional phrase attachments. But they weren't huge. And then lastly, which I actually think is one of the biggest strengths of this, is that you have no headaches from thinking about how to combine the outputs from these multiple systems. Because most of the time when you're doing parsing or named entity recognition, you really are planning to use it as input to something else. And now you just know that everything is consistent and you don't have to deal. All right, so there's a saying in NLP, there's no data like mo data. And so like I said earlier, the joint data that we have they're much smaller than corpora that have just named entity and just parse information. And so, the numbers that I got were a lot lower because I was training on a lot less training data. And so one obvious question that you can ask is how can I incorporate all of this singly annotated data into my joint model? How can I use things like the Connell named entity data set and the Penn tree bank to improve the joint model? And so that's what I'm going to talk about now. And so one problem is that you can't just throw the data in because each model has its own representation. And so if you were to try to throw in, so this is using the ties to Osama bin Laden example, if you were to throw in just the parse tree version of that doesn't have the named entity information, you're going to confuse the model because it's going to think that Osama bin Laden is not a person here, right? If you take the named entity data, there is no syntactic structure, so I don't even know how you would just throw that into your model, but however you throw it in is not going to be happy. And then, you've got the joint model that actually has all of the information. So while we can't just throw the data in, we can observe that the joint model shares features with both of the other models. And so these are the four features that we had before. And you can see, so the first one is prepositional phrase goes to preposition, and then a noun phrase that's a person. That's a joint feature. It's only going to occur in the joint model. You're never going to see that in a parse model or a named entity only model. But the second two both deal with only the syntax. So prepositional phrase goes to preposition, noun phrase, or just the root as a preposition. That's going to occur in both the joint model and the parse model. And then that last feature that says Osama bin Laden is a person is going to occur in the joint model and the named entity model, but not the parse model. And so we can share information by the use of features even if we can't just throw all of the data together. And so now to discuss how to do this, we're going to get a little bit more technical. Oh, I meant to do that, sorry. Oh, and another thing to observe is that you would hope that you're going to learn similar feature weights in the models that where the same feature is present in both. It's not going to be identical, but hopefully they'll be somewhat similar since they should be indicative of the same kinds of things. And then you just basically don't learn any weight for the features that don't exist. They effectively have a weight of 0 because they don't mean anything. All right, so here's an actual equation, a very generalized version of the equation for the things that we're trying to optimize. And so the first thing that we have is our model, and then we have a prior over the parameters. And so here we're saying, okay, we've got P of y, condition on x parameterized by theta. And so y is whatever the thing we're trying to learn. So it can be the joint structure or the parse tree or the named entities. And then the x are the observations or just the words in the sentence. Those are going to be the same for each of the models. And then the theta are the feature weights, which are the thing we're trying to learn. And so typically when people build a model, they also put a prior over their feature weights. Normally it's just going to be a Gaussian prior centered around 0 with some kind of variance that tells you how much you want the feature weights to vary from 0. And so what we're going to do is we're going to change that prior, and that's how we're going to link everything. And so here's a graphical representation of the same equation. The variables mean the same thing. So once again, x is the sentence, y is the parse tree, theta are the feature weights that we're trying to learn. And then mu and sigma are the prior, mean, and variance. Like I said, normally mu is 0, but in theory you could set it to something else if you wanted. And so what happens is we effectively have 3 of these little graphical models, one for the parse model, one for the joint model, and one for the named entity model. And what we're going to do is we're going to erase the mu's. We're going to erase that mean, and we're going to link everything via a hierarchical prior. And so now we have a top-level theta, and then a bunch of low-level thetas for each of the individual models. And when we optimize this, we're going to optimize the top-level theta as well as the lower-level thetas, even though we only end up actually caring about the feature weights that we learned in the joint model. And so what happens is, if you have some feature that, say, you have a lot of evidence for in the name model, but little to no evidence for in the joint model, then the weight that you learn ends up getting propagated up to the higher level prior, the higher level theta, which then gets propagated down to the joint model. And similar for the parse model down to the joint model, because we're using a lot more parse data and a lot more named entity data. And so there's going to be a lot more features that we've seen and that we have a lot more evidence for in the individual models in the joint model. But this allows us to link them so that the joint model can learn good weights for those features. Well, on the other hand, if there's features that it has a lot of evidence for, it's also free to ignore the prior, which is influenced by the individual models.
Why is sigma replicated but mu is not?
Why is sigma replicated but mu is not?
You have sigma on both the big theta in the sky and also on all the sub cases, but you don't have the sigma mu.
So you're saying, like, why don't I have a big sigma up here that's also pointing to everything?
No. Why did you erase the mu from the lower sigmas, but you didn't the lower thetas, but you didn't erase the sigma from the lower thetas?
Because the thing that because what I'm doing is I'm centering this theta around that now, which it used to be centered around mu.
So the big theta in the sky is playing the role of the mu.
Yes, the big theta in the sky is playing the role of the mu. Thank you.
And the mu is the meta-god, right? It's the bigger theta in the bigger sky, right?
Yes, that is correct.
So now, is it the case that the lower thetas in the non-joint models just don't care about the features that will never occur for them?
So features that never occur to them, just like it. I mean, you can set it up however you want so that they get whatever weight, they basically get completely influenced by the prior, or you can set them to 0, but it makes no difference in what ends up being learned in the joint model, and because those features never occur in the data because it's impossible for them to occur, it just never uses them, so it's sort of irrelevant what they are.
So it doesn't push them towards 0, okay.
No, it doesn't push them towards 0 because there's no evidence at all pushing back, so they're just strictly influenced by the prior, and that's it.
Yeah, okay.
Yeah.
So is this intuition correct? So the theta on top is kind of, these are the feature weights I should use if I had to use the same feature weight in all 3 models.
That is correct.
And then and so you have a prior, mean, and
variance for that.
And then for each of the individual models, you're saying, but I've learned from my data just from this model that I ought to vary each feature weight by so much.
Yes.
From its value.
That is correct.
Okay.
And the one other intuition that I want to give you is about the lower level sigmas versus the higher level sigmas. I think it's important to note that they actually play very, very different roles. And the top level sigma is what you normally think of as a sigma, and it's the one that says, how much do I dislike moving away from 0? These ones say, how much do I want to share information between my different models? How much do I want to trust my evidence versus the prior? And we did end up using different values for the low-level sigmas and the top-level sigmas, which is not surprising since they're serving such different functions. And we're actually...
Did you use the same sigma in all 3 subfunctions?
Yes. I tried a little bit with varying it based on things like the amount of data, and I couldn't figure out anything that worked better than just setting them all to 0.1. So that was what they all got. Okay, so the extra data provides other additional benefits, mostly with respect to the grammar and the feature set. And so before I was talking about the grammar and the fact that you normally just read the grammar rules that you've seen off of the data. And so now just because you've seen more data, you've seen more rules that are probably useful that maybe you didn't see in the small data set. And so you can share grammar information between the joint model and the parse-only model to get a better grammar. And then similarly for the feature set, lots of the times there's going to be features that, say, only occurred in the named entity only model and just never appeared in the joint model, even though the joint model could, in theory, use those features. And it's going to learn a weight for them. because of the fact that it's being shared by that top level theta. And so it's going to just have a lot more features available to it that it's learned some information about. All right, so does it help? So here's the same. So this setup was just to give you the actual experimental setup here. We're still using OnToNotes, and I stuck with all of OnToNotes because I did want the annotation schemes to be consistent between them. And so for each of the different sections here, the additional parse data was gotten by combining the remaining 4 sections, only looking at the parse information and ignoring the named entity information. And then the extra named entity data was from the CNN portion of the corpus, which was the largest portion of the corpus, which is why there's no CNN set of bars. And so that's the experimental setup. And so you can see that it helped the named entity. This is once again the named entity recognition results. And so I've got the baseline NER and the joint model, which are the same as they were from the previous slide. And now we also have the hierarchical model. And so you can see that it helps, I think, quite significantly. I think the biggest reduction in error here was about 24%. Once again, not surprisingly, it helps more when you have a lower baseline than when you have a stronger baseline. For PRI, which is Public Radio International, the hierarchical model actually degraded performance slightly. On the development data, it helped. So I'm actually at a loss as to why it went down a little bit. It wasn't a lot. It was only, I think, about 1% or 2%. But there is a decrease there. But overall, in sum, it's definitely a significant increase. So we got a 20-something% reduction in error from doing the joint model, and then another 20% reduction in error from adding the hierarchical and then the extra data that you could get that way. The parsing performance, so if you remember from before, the parsing improvements from the joint model weren't that strong. They were very small. Here we got much better parsing improvements. And once again, it was in the low 20s was the reduction in error. And the smaller corpora are going to get bigger gains, but all of the different sections got statistically significant gains from adding the extra data in.
So that's because the added data in this case is the entry, right?
So the added data is, for the parsing, it's from the remaining sections, and from the for the named entity, it was from the CNN. We didn't use the Penn tree bank because it is a somewhat different annotation scheme. And so I think the issues that you would have from the change in the annotation scheme would have probably overridden the gains you would have gotten from the extra data. So I would definitely like to experiment more with how do I also get improved performance when I'm using things that are annotated differently but with the same intent. But I haven't had a chance to play with that. And another issue, for if you want full disclosure here, is, discriminative parsing is kind of slow already. And then when you add in named entities and increase the state space, it gets slower. And so to actually be able to run it in a reasonable amount of time so that I could do, future development and everything, I did want to stick with somewhat smaller corpora.
Slower training time.
It's slower training time.
Decoding time's the same, right?
So,
Decoding time.
No, decoding time is definitely also slower.
Is it?
Yeah, because you're still, the biggest reason why it gets slower, there's a lot of them, but the biggest one is just that at the very inside of your many levels of nested loop is the feature computation.
Oh, right.
And that's slow, and it's too, and at training time, it's like too big to actually store it on disk also. You actually have to recompute them. It's like, I learned way more about things like serialization and memory management than I ever wanted to know. But the point here is that adding the extra data does in fact help, rather significantly. Okay, so holistic processing across tasks improves performance. So standard approaches to things like named entity and parsing throws away a lot of information because you're only looking at individual tasks, and as a result, you do worse. And so the full joint model over multiple tasks improves performance on both of the tasks. And it also gives you a more consistent and more easily usable output because the thing that you get out is just, it's consistent, it all makes sense together. And then the use of a hierarchical prior allows you to use additional previously unusable data to further improve your performance. And then going back to the example that we started with, the joint model does in fact fix all of the errors that we had here. And so now it's got that Egyptian Islamic Jihad is an organization. It got Osama bin Laden as correctly being a flat structure. And they got this prepositional phrase correctly attached to members now instead of the jihad. So moving on to the third part of the talk, holistic processing across datasets, or multi-domain learning. And this is the shortest section by far. And so the motivation here is that we want models which are going to perform well across all genres of text, right? We have huge amounts of labeled financial newswire and labeled other kinds of newswire, but a lot of the time you actually want to run it on things like web data or email that you're going to have a lot less data for. And so the hope is to somehow build something that can help you do just a better job in general. And so similar to the hierarchical model that we had in the last section, the idea here is that each of these different domains is going to have some set of features and some set of feature weights, but a lot of those features are going to be the same, and so you can link them, once again, via a hierarchical structure. And so here's like literally the exact same picture that I showed you before, except that I've changed the labels to now say American Newswire, British Newswire, and blogs, and you link them via the exact same kind of hierarchical structure. And here what ends up happening is, in theory, all of the features are shared across all of them, unlike in the other case. But what ends up happening is that if you have a feature that's present in one domain, and you have a lot of evidence for it, then you're just going to go with the evidence that you have, and basically that evidence will override the prior, and in fact will influence that top level theta. While on the other hand, if you have a feature that you have little evidence for, then hopefully some other domain had a lot of evidence that influenced the high level theta, which then influences you, and so your opinion of the feature weight just comes from the other domains instead of from your domain. And then these thetas, once again, tell you how much the information is being shared. And in fact, if you set theta really low, which means really strong regularization, that's the same as just lumping all of your data together, just concatenate it into one corpus, because you're effectively saying they all have to be identical. And if you make the sigma really high, that's very little regularization, and it ends up being equivalent to just training each of the domains completely separately. And so what you want is somewhere in between those. So you have some amount of sharing, but not too much. And so in the experiments that we performed here, we used the Connell data. So this is named entity recognition, and we used Connell, MUC6, and MUC7. And we compared to training on just the single domain, training on concatenating all of the data together, and then training using the hierarchical prior that I just showed you, so the multi-domain learning. And as you can see, it improves performance across all of them, based on compared to both of those baselines. Connell was the largest corpus, so not surprisingly, it got the smallest improvement. But MUC7 got a pretty substantial reduction in error there, and so overall it works. Is that a question?
Yes.
Yeah.
Do you tune your sigmas to optimize likelihood, or do you tune your sigmas like during sampling, or do you tune them to optimize accuracy on some LDAP set?
The last. So it was basically hand tuning on development data, and I ended up with. For the top level sigma, which is just a normal sigma, 1.0, and for the bottom one, 0.1 again. I mean, once again, you can vary it a little bit within that range, but roughly 0.1 is what you want.
Relatively smooth kind of parabola that starts at the multi-domain and ends at the concatenate data or something.
I mean, the truth is I didn't run it through the whole range because I was just trying to find the best, and it didn't actually occur to me to try to plot the entire thing out. But that would be interesting. I wish I had done that, but I.
It's basically saying concatenate data, right?
Yeah.
And if you push towards infinity, then it's basically
yeah. All right, so to finish up this part, so holistic processing across data sets improves performance. And so the motivation was that we want to do well on all genres of text. And we can once again use this hierarchical prior to link the different data sets and improve performance on all of the corpora. All right, so conclusions. All right, so what have we accomplished? So first I talked about holistic processing across sentences, where the question was, how do we integrate non-local information when making a decision? And the answer was to add long-distance links to a state-of-the-art model, and to now use Gibbs sampling to reason in that model. And this allowed us to label words and phrases consistently. For the second section, I talked about holistic processing across tasks, where the question was, how do we integrate multiple levels of information? And the answer here was to directly model the relationships between the different layers of information. And this provided you with a consistent and easily usable output, as well as higher quality output. And then the use of the hierarchical prior allowed you to use extra data to further improve performance. And then the third question was holistic processing across data sets, or how do we build robust systems which work well in many different domains? And once again, we used a hierarchical prior to share information between the different domains, and we found that we did, in fact, get performance over reasonably strong baselines. All right, so what's left to be accomplished? So, one obviously that comes to mind is combining all these different kinds of holistic processing. And so in the joint parse NER model that I described, I wasn't adding long distance links between different kinds of different phrases that were the same. And I could have added another level of hierarchy to do domain adaptation between the different sections of Notes, but I didn't. So just combining all the different kinds. The second one is, a big joint model of everything. So joint parsing, named entity, co-reference, word sense, et cetera. I'm trying to add coreference into the model right now, actually. I'm in the early stages, but I'm hoping to get that done. But I think it would be, really fun to have a big joint model of everything, but obviously only if you can actually improve performance with it. Don't do it for the sake of just doing it. And then the next one is something that I view as somewhat more of a long-term goal. I mean, I think the first two are more hypothetical. This is something I'm actually really interested in. And so, the claim that I'm making at the beginning of all this talk is that, we need these core processing tasks so that we can do a good job at the high-level tasks that humans actually care about, right? We want to do a better job at question answering or machine translation. But we continue to evaluate things like named entity recognition based on F1, when really the question that you have is, if I take this named entity recognizer and I throw it into my MT system, is my MT system going to improve or not? And so, the first step is just to actually do task-based evaluation. I think it's I understand why it doesn't happen because it's, kind of a pain to do, but I think it would be really important, especially when you're getting things like a 2% gain. There's just no guarantee at all that it translates to improved performance in reality. And then I think much more interestingly would be to do actual task-based optimization. So figure out how you can optimize your low-level models to actually do a better job as opposed to just checking to see if they do a better job. And then the last thing, which is what I view as my sort of shorter term future work, is improving model quality through the use of large amounts of unannotated data. And so I think, a lot of people fall into either, supervised learning or unsupervised learning. And I definitely think that the future of NLP is in the middle and it's in semi-supervised. And I think, for supervised learning, the appeal is obvious, right? You have labeled training data and supervised learning does better than unsupervised learning, plain and simple, but like the unsupervised people like to complain, annotating all that data takes a lot of effort. And, is it really worth it? Is the information already there? And so I think that it's true that annotating a lot of data requires a lot of effort, but annotating a little bit of data really doesn't. And you need to incorporate a bias into your model somewhere. I mean, if you don't annotate a little bit of data, you're just going to spend forever figuring out your unsupervised model. And so it seems to me that the right approach is to just, be in the middle of the road and do something semi-supervised where you're willing to label some, but you can still use, the entire, web scale corpora to further improve performance. And so that's the stuff I'm interested in working on next. And so that's it. Questions? And I guess you asked a lot along the way, so.
The previous slides.
Previous slide?
What's the distantly?
Oh, so distantly supervised learning, what I mean by that is things where, so to give an example, something like in Wikipedia, they just have lists of locations. How can you use that to improve your named entity recognizer? So it's finding naturally occurring data that has some amount of labeling, but like naturally occurring labeling that's relevant to your task, and how do you use that? So it's not just raw text, you know something about it, but you didn't sit there and annotate it yourself or pay someone to annotate it yourself, or annotate it themselves.
Regarding the way you do the hierarchical model with the Gaussian priors, have you thought of having priors that have non-diagonal variance, something like that? That you want to say that the features, it's still all of those priors assume that features are independently moving.
I think sort of is the answer. So I've been working with one of the first years on that project his main interest is trying to automatically learn the sigmas, where you can you can link different groups of sigmas. So, when we say features, frequently we actually mean feature templates. So when you say the word, that's not a feature, right? That's like going to be a couple of thousand features. And so maybe grouping them together and then learning the variances for the groups of features independently, or just learning it for all of them at once if that makes if that does a better job. But trying to actually automatically learn the sigmas is something that we're working on right now. But so far it's sort of been, the thing is, a lot of the ways to do it, because we're using stochastic optimization also, there's just like a lot of like levels of, what am I trying to say here? Like we got it working when we were using really toy data sets and doing exact optimization, but with the stochastic, it seems like it's a bit noisier, and so it's not working as well, and we've been trying to figure out why, but I haven't figured it out yet. Thanks.